Hi there, future professional engineers. This is Wasim Asgar. I'm a licensed engineer in the US and Canada. I've authored several books on the topic of FE electrical and computer exam preparation and PE power exam preparation, and I also run popular programs for FE electrical and PE power exam prep. In this video, you're going to see me doing a strategic overview of section number 15 of the FE electrical and computer exam, which is digital systems. Digital systems is a heavy hitter. It is one of the big 5 topics on the exam. These big 5 topics collectively make up about 50% of the exam by weightage. And that's why it is really important to give them the due attention, put in the necessary time and effort, because they have an outsized impact on your exam result. Now, digital systems in particular is a challenging topic because a lot of folks who are taking the FE electrical and computer exam plan on taking the PE power exam and they have a power systems background. As a power systems engineer, you don't deal with the concepts related to digital systems on a regular basis. Moreover, there are some topics in digital systems which are inherently very difficult, such as flip-flops, counters, timing diagrams, multiplexers, encoders, decoders, and so on. In this video, I have included the extract of the live training session that I conducted with my students for FE electrical and computer exam preparation program, and you're going to see me break down digital systems into smaller chunks, and I will also share practical advice as to how you can deal with the individual topics that form part of digital systems. The fact of the matter is that not everything within digital systems is super difficult. There's some easier low-hanging fruits in digital systems, and you should make an effort to actually capitalize on them. And even the more difficult topics within digital systems, if you actually approach them in a proper method, then they can become a little bit more manageable and easy. If you're new to this channel, I would really appreciate if you could like this video and subscribe. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation, and I also touch upon topics related to power systems and electrical engineering. If you have any comments, suggestions, feel free to mention them in the comment section of this video. Without further ado, let's dive into the content. So let me do a quick review of digital systems. Now, digital systems, section number 15, is the last of the big 5 topics, okay? And it is very important for us, as we've been talking about the big 5 topics, to pay special attention to these sections because of their outsized impact on the overall exam due to their weightage. On average, roughly each one of these big 5 topics, math and circuits are actually the 2 biggest, if I'm not mistaken, within this category. But for simplicity, let us assume that each one of these big 5 topics is roughly 10% of the exam. So the first 5 sections, not the first 5, but the big 5 sections account for 50% of the exam by weightage, okay? Now, arguably, the most difficult section within this big 5, based on the feedback from my students when they go through the program, when they complete the surveys, the number of questions they ask, the type of questions that they ask for clarification and whatnot, I generally find that digital systems is the most challenging for most of the students. And the reason, as I mentioned previously, is that a lot of students who are taking the FE exam, pursuing the P license, are directly or indirectly related to power systems. Okay, whether you're working for an MEP, for a utility, on the client side, whether you're working for a municipality, for a public project or whatever, it's typically power systems engineers. And once you've entered the workforce and started working as a power systems engineer, you really have nothing to do with digital systems, correct? Only if you're working in computer systems and hardware design, then, or chip design maybe, then you might encounter these type of concepts. But even then, it would be more application-based rather than theory-based. Anyways, so due to these reasons, students find digital systems challenging. Now, the way that I recommend you to approach digital systems is to actually look at it in terms of mini milestones, okay? Divide this section up into individual topics. So the first topic, for example, that we encounter in digital systems is number systems. So we need to know binary, octal, decimal, hexadecimal conversion between them, okay? And I've gone through detailed lecture explanations in lecture problems, several practice problems, quizzes, where we have done all different types of conversions. Your calculators can actually do these conversions, but sometimes it can be limited, right? I don't think the calculator does the decimal. It does not handle the decimal, correct? So when it comes to decimals, and you're going back and forth between these number systems, then there's a different technique that you have to apply, which we've discussed in the course. So those type of things, keep an eye on it. And if the opportunity rises where you can actually use the calculator directly, then by all means, use the calculator, save time and potential mistakes. Okay, so number systems also include ones complement, twos complement. The details that are in the reference handbook, when it comes to digital systems, they only have 2 pages or 1.5 page of content for a big five topic, right? So about 10% of the exam, you're extracting from those 2 pages of references. One's complement and two's complement is defined in the reference handbook, but it is not defined in an easy to understand terminology language. Okay, so within the course, we've done multiple practice problems. There is the issue of the carryover, right? There's the issue of identifying whether this is one's complement, two's complement, right? There's an issue of multiple zeros, a +0 and a -0 in one's complement, two's complement takes care of that. So all of those fine details, make sure you go through those practice problems and have that framework properly well understood. Okay, so that's number systems. On average, I would say it's actually on the easiest side of things. Then we have Boolean logic. Now, Boolean logic, the amount of detail that is provided in the reference handbook, it is minimal, right? There are a lot of Boolean identities and logic. The ones that we have used in the mini exams and the quizzes, they're very broad range, right? The Boolean logic that we have in the reference handbook primarily focuses on De Morgan. De Morgan itself can be sometimes tricky if you don't know how to apply it. But my recommendation is that get yourself acquainted with other Boolean logic identities, right? Other laws, other theorems, and they can help you when you get stuck. Now, whether you need to memorize them or when you go through enough practice problems in the quizzes, in the mini exams, study guide, homework assignments, they'll probably become second nature to you, right? But proper application of Boolean logic can make it or break it for you, especially in the easy sections of digital systems, because it is not that Boolean logic shows up in one section only, right? Or in one topic. Boolean logic, you may have to apply it in flip-flops, in counters, in multiplexers, okay? When you have taken the Kmap minimization as far as you can, and then you may actually have to get into Boolean logic. So this is a very, very important tool to understand and to practice and learn, okay? Logic gates. So logic gates and circuits, you can be given a circuit and you may be asked to sort of create an output out of it, right? And then maybe even minimize it. Or you may be given a function and then translate that into a circuit. There's so many different ways to approach it. But at the end of the day, you need to have, first of all, start out with the wide range of basic fundamental logic gates that are found in digital systems and understand their truth table, especially the truth table of exclusive OR and exclusive NOT. They're not very intuitive, okay? Other than that, AND is pretty simple, OR, NOT, NAND, NOR, they're fairly simple. But these logic gates can also appear as timing diagrams, right? We've done some practice problems where we have multiple logic gates and we have inputs and the clock coming up, right? And there is a time delay. And if the time delay is not accounted for, then the output can actually be incorrect, okay? Logic minimization sort of goes back to logic gates and to Boolean logic, but the new thing over here is Kmaps. Now, Kmaps have multiple steps, which I've discussed in the lectures. First of all, translating a function and putting it on the Kmap, right? Whether it is a 3-variable or a 4-variable Kmap, that is arguably the most important step, because if you're not able to translate the function onto a Kmap, then you're basically fighting a lost battle already. Okay, so that is the most important step. All right. Once you have the Kmap mapped out, then you have to identify which groups or sets of ones are adjacent, because we can actually create groups in powers of 2 only, right? So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. Okay, so this is 1, this is 2, this is 4, this is 8. Where I find students struggling the most is that they have incorrect understanding of which ones are adjacent. The simple definition of two adjacent ones is that they will only differ in one variable. Okay. And we've gone through some examples, right? These two ones are actually not adjacent in terms of our Kmap. These two ones are adjacent, right? So it's not that they're boundary, they're sort of touching, because these two ones are going to be different in more than one variables, right? And then obviously all of those observations that the ones that are at the corner of a K-map, they sort of wrap around, they form one group of four, okay? The columns at the end, the rows at the top and the bottom, they fold. So you have to go for the largest groupings of one. And it's not the end of the world if you're not able to identify the largest grouping, but it will make your life very difficult. Because let's say you fail to identify a group of 8 and you consider it as a group of 4 and a group of 4, then in order to combine those two groups of 4, you will have to use what? Boolean logic. And I explained you guys in the lectures, in the live training, that the Boolean logic that you may have to use in order to sort of reconcile that may not be very simple. So the easiest way to approach this is to actually do the K-map setup properly and to come up with the largest groups of one and minimize it using K-map. Okay. And we have tons of practice problems in the course to work through that. Flip-flops and counters. So the three different types of flip-flops that we have encountered in the reference handbook are SR, JK, and D flip-flop. There's also another one very commonly used called the T flip-flop. We don't need to worry about that. To understand their characteristic tables, right? SR and JK flip-flop are basically the same. The only difference is that JK handles that unique case where set and reset are both equal to 1. It simply toggles a previous input, and we've done quite a few problems. And D flip-flop is by far the easiest one. Whatever shows up in the input actually shows up at the output as well. Okay. Now, understanding their own table, characteristic tables, or truth table, whatever you want to call them, is the starting point, because that is already given in the reference handbook. It really doesn't require any special visualization, imagination. But dealing with that in terms of transition, clock transitions, combining that and overlaying it on top of how the digital circuit is designed based on the input output connections, initial conditions, and state by state transition for each given clock, that's where the magic happens. Okay. Now, if even you have a two flip-flop circuit, right, a counter, the issue is that in most of the cases, when you take all of these steps, creating the truth table and going through the transitions, clock transitions and whatnot, it is generally not a 3-minute problem. Okay. So counters and flip-flops are most likely going to be a 5-minute problem if you want to do it right. And if you don't have the time to do it right, trust me, the chances of you getting the right answer are next to nothing. Because even if one of the bits, one of the states you incorrectly switch, everything downstream, it's not going to work out. All right. So you have to be very patient, very focused, and very detailed and calm when you're solving these type of problems. Okay. So my recommendation is that everything that we've discussed up until this point, right? These guys are 3 minutes or less. Okay. But there are a couple of items in here that are 5 minutes or more. So when you're going through digital systems, make sure you do all the 3 minutes or less problems upfront and leave the 5 minutes and larger problems only when you have time left over. This will ensure that you are able to deal with the difficult problems in due time if there's leftover time. At the same time, you've actually converted the easy problems, hopefully, into points. Okay. And in the lecture, I have detailed makeup. Like I have basically gone at the level of latches in order to explain you how the flip-flops are created. So if you go through all of the on-demand content related to that, right, and do a bunch of practice problems, I think you'd be more than comfortable. In fact, if you look at the sample exam, the paperback sample exam for FE Electrical and CS, after going through my on-demand content, you're going to find those problems relatively easy. Okay. Then we have programmable logic devices and gate arrays, PALs and PLAs. One has both the OR field and the AND field programmable. The other one just has, the OR field programmable. The AND field is not programmable. It's a combination over there. You just need to equip yourself with the working, and it should be fairly simple, straightforward. State machine design is fairly simple, straightforward. You need to basically go back and forth between the state diagram and the state table, identify when the outputs basically show up, and handle those transitions carefully. So I believe that these are also 3-minute or less. Okay. Now, when we deal with timing diagrams, things can get tricky. So a timing diagram problem can be a relatively simple, straightforward problem, right? Or it can sort of, as we've done some of them in the homework assignments, basically overlay on top of a logic circuit, which would have multiple gates, right? And then for each gate, you have, different types of time delays. And then you'd have to carefully walk through each and every one of the gates, identify how much of a delay it's encountering, and then accumulate that. And depending on how the question is asked, you would have to answer that, right? So I would say that the flip-flops and counters, 5 minutes or more, and the timing diagrams, 5 minutes or more, right? So these two guys, flip-flop counters, timing diagrams, are arguably the more difficult topics, okay, within digital systems. And you can throw multiplexers and decoders and whatnot in there as well. Other than that, the rest of digital systems is very, very doable, okay? And the more time and effort that you put in, the more comfortable you're going to get. I know for a lot of people, digital systems presents what we call as the fear of unknown, right? Because you may have only taken one course in your undergraduate coursework, and that might have been 10 years ago, correct? And since then, you actually have never ever looked back at digital systems. So for all practical purposes, you are learning this from a blank slate. And that's what I've assumed in the program, right? When I work through the content step by step and divide into multiple parts, lecture series, and the supporting homework assignments and whatnot, that's the intention behind it. That even if somebody enrolls in the program, has zero background in digital systems, at least that person can become comfortable within the context of the exam. Okay, so this is the strategy I'd like you to review. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE Electrical and PE Power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the PE Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.